As shown in the figure below, a top steadily precesses about the fixed direction z at omega equals 67 rpm. Treating the top as a cone of radius 1.2 inches and height of 2 inches, find the rate of spin psi dot of the top about its axis of symmetry z in radians per second, also given alpha is 29 degrees. Now, this problem is no joke, and it's really a culmination of all of our dynamics skills, but where would we even start? It's always good to visualize a problem and search for ways to simplify its components, so let's begin by identifying reference frames which might be useful in making the problem easier to solve. First, we have the Earth fixed reference frame, which we'll call A, and it's rotating counterclockwise about its z-axis with an angular velocity of omega. For this reference frame, let's use the unit vectors I, j, and k for the x, y, and z axes respectively. Next, let's look at the top fixed reference frame, which we'll call B. It's been rotated about the x-axis from reference frame A by an angle of alpha, and it's rotating counterclockwise about its own z2 axis with angular velocity psi dot. We'll use unit vectors I2, j2, and k2 for the x2, y2, and z2 axes, respectively. Lastly, we'll note that the top is going to be idealized to be a cone for simplicity, and although it doesn't matter, we'll assume its mass to be 1 kilogram. Okay, so with these reference frames, the equation that we'll use to solve for psi dot is the following. The moment in reference frame B is equal to the angular acceleration of reference frame B plus the angular velocity of an intermediate reference frame A crossed with the 3D inertia tensor in reference frame B times the angular velocity of reference frame B. To clean this up a little bit, we'll note that the angular acceleration term will immediately go to 0 because we're told that reference frame B has no angular acceleration. And additionally, the brackets with subscript B denote that we'll express that specific quantity in terms of the coordinate system of B. With all of this set up, let's look at each of these terms individually. The first term is the net moment in reference frame B, and we're told that gravity is the only contributor to this value. Recall that the moment can be calculated by Rf sine of alpha, where r is the distance from C to the center of mass of the object, and F is the force of gravity. A cone's center of mass is located 3/4 of its height from the tip, so r would be 2 times 3/4, or 1.5 inches. The force of gravity is m times g, which comes out to 386 kilograms times inches per second squared. Lastly, alpha is 29 degrees, and when we plug all of this in, we get that the moment generated by gravity in this reference frame is 280.769 kilogram inches squared per second squared in the negative I2 direction. The second term is the angular velocity of reference frame A in terms of the unit vectors of reference frame B. From basic geometry, we can see that this is simply equal to negative omega sine of alpha in the j2 direction and omega cosine of alpha in the k2 direction. The third term is the 3D inertia tensor of a cone, and because of our reference change, this matrix is simply a diagonal matrix with no products of inertia. The inertia about the x and y axes is 3/5 mh squared plus 3/20 mr squared, and the inertia about the z-axis is 3/10 mr squared. The fourth term is the angular velocity of B expressed in reference frame B, and initially one might think that it's simply psi dot, but upon closer analysis we realize that not only is the cone spinning about its own z2 axis, but it's also revolving around the z-axis from reference frame A. So we must add the components of omega to psi dot. This results in negative omega sine of alpha in the j2 direction and omega cosine of alpha plus psi dot in the k2 direction. Now that we've established all of the terms of the equation, let's plug everything in. In its current state, this equation is a little bit overwhelming, so let's simplify. First, computing the matrix product. Next, let's do the cross product. At this point in the solution process, it would be a good idea to input our given values into this equation. We're given that omega is 67 rpm, which is about 7.016 radians per second, alpha is 29 degrees, and the cone has a height h of 2 inches and a radius r of 1.2 inches. Putting all of these values in yields the following. And finally, solving for side dot gives us that the angular velocity of the top in reference frame B is 222.09 radians per second counterclockwise in the K2 direction.